Hi everybody, welcome back. Well, I hope everything's going well with all of you. It's been pretty crazy here with getting my son back into college. My new grandson, is over. I'm trying to get as much grandson time as I can in between everything else going on. But I just want to open up by saying this is going to be kind of a cobbled together mess of video because I shot these clips over so many days and so forth. But it was a very interesting journey, and I think the way this turned out was pretty good. I do want to address one thing at the very beginning here. I had a few comments about the modification that I did on this thing for the bias circuit. And one of the questions was, and this is a good question, if we pulled one of the vacuum tubes, one of the 12AX7s out of the amplifier while it was turned on, would the excessive current going through those Zener diodes, and you're going to see what I'm talking about here, would that cause the Zener diodes to go up in flames? Well, as far as I could tell, no. And the reason I say that is the filament of a 12AX7, if you run it on 12 volts, so you have the two, each 12AX7 has two filaments. So you'll see there's one on this side and one on this side. And each filament is 6.3 volts. The filaments are wired between pins 4 and 5. And then if you go to pin 9 is that center tap where the two go together. So if you jumper 4 and 5 together with pin 9, you can run them both on 6.3 volts, or you can just go from pin 4 to pin 5 and run them on 12.6 volts. If you run them in 12.6 volt mode like that, they're going to draw about 150 milliamps of current. So there'll be a 12.6 volt drop across this filament, and it will be 150 milliamps of current. So if you do the math, 12 volts times 150 milliamps is going to be about 1.8 watts of dissipation. And I used a 5-watt Zener diode. Now that does not mean that those Zener diodes will not run blistering hot when that happens. But chances are as long as you don't run them for a long period of time, it probably won't hurt it. And I had another interesting question about the resistance. Somebody had measured the DC resistance of the filament, and when they tried to calculate the current draw, they miscalculated it. And the main reason is the current or the resistance of the filament when it's cold is much different from the resistance when it's hot. So when it's cold, it's less than 10 ohms. But if you do the math, these things run at 150 milliamps. They dissipate 150 milliamps of current at 12.6 volts. And if you do the math, so we'll say 12.6 volts divided by 0.15, yeah, 84 ohms. So it's 84 ohms. So if you put those three, because they said, why is there a 400 ohm resistor in parallel with three less than 10 ohm resistors? That 400 ohm resistor is doing essentially nothing. Well, actually, the hot resistance is 84 ohms, and if you times that by 3, you're 250 ohms or more. So in that 250 ohm range, you put a 400 ohm in parallel with it, well, that is a difference. So just wanted to go over those couple of things. So rather than carrying on here, let's get on to the video. Like I said, it's going to be a cobbled together mess of clips, but I'll try to arrange them in an order that they make sense. We found out some very interesting things about the way this bias circuit works and some of the differences between the different types of tubes that we tried in here for the outputs. The 5881, the old style versus the new style ones. The EL34 we tried, and we rewired one of these amps, and the 6l6gcs, 6l6gbs. So we're going to talk about all that in this video. So if that sounds interesting, stay tuned. That's what we're going to do, and hope you like it. So if you recall in the last video, we actually went through and redrew the schematic to make a little more sense of what was going on in this circuit. And we determined that this amp acts more like a cathode biased amplifier than it does a fixed bias amplifier. Even though you have a bias voltage, a negative bias voltage going onto the control grids here on pin 5, it doesn't matter because you also are floating this cathode, this voltage drop above the actual return point. This return point, okay, well, even though we're not calling it ground because we're grounding the chassis at this point here, this is truly not 0 volt return. This is, the chassis is actually floating at about 36 volts when everything's working properly, give or take, above your common. So you can see when you measure from here to here, it's going to give you a negative 36 volts. We talked about this in the last video. And of course, the problem was this whole setup was based upon the EL37 type vacuum tube that the amplifier was originally designed for. And you can, if you remember in the schematics, the original schematics we have, the schematics are even calling for something more ridiculous, which is KT66/EL34. And those are very, very different valves with very, very different characteristics. We'll talk about that here in a second. So what we ended up doing was the final vacuum tubes that I put in here were 6L6GC. Those last two letters are very important because 6L6 doesn't tell you the whole story. It only tells you part of the story. There are different versions of 6L6 tubes. There's a straight 6L6, there's a 6L6G, 6L6gb, 6L6gc, and then all the later versions which are variants of the 6L6gc. So these are 6L6, they call them EH, which is Electro-Harmonics, which is the manufacturer, but these are really very closely related, almost an identical copy of a 6L6gc. The tubes that were in there were these 5881/6L6WGBs. Now what's the difference? Well, let's see if I can burn my fingers on this tube because they've just been sitting here hot. And if I can do this without burning the crap out of myself, if you look at these two tubes, you can see that the actual, this gray part is your anode of the tube. And you can notice they are different. They are different in size, but they are very similar in shape. Okay, so they're different size. These 6L6WGBs have a lower power rating. So in other words, the anode can dissipate less power, less wattage, than the big brother 6L6GC. Now, the bias points and things are similar, but how much plate dissipation you could set these to is higher on these. And that worked out to the advantage of the final design we had here. So our final design was this. And what we did was we changed this voltage divider a little bit between, or this current divider circuit here, between the filament string, which has to be 36 volts or somewhere around there for the 12AX7s to work properly. And we modified it by changing that resistor to, we ended up with a 2.2K, and then we had a 12 volt, 13 volt, 12 volt, if you remember, set of Zener diodes. So it can, this thing can top out at around 37 volts, give or take a volt in here. That was not enough bias. So what we did was we floated it a little bit higher by putting this 75 ohm resistor in here and a 12 volt Zener diode to clip that off. So this will give us about a 39 or a 40 some volt So like 40, what is it? 37 plus 12, which would be about 49 volts. You need to be somewhere around that 50 volt range for a 6L6GC to be happy where we were. And that's what this gave us. So that ended up working out pretty well. These tubes are idling at somewhere around between 17 and 18 watts. And and you can see when we drive the amplifier, we can get our 25 to 27 watts output like it's rated. In addition to that, you can bypass this. You could actually return the circuit to this design here. These 6L6GCs will probably take the added bias, even though they're running a much hotter. However, what will happen is you're not going to gain anything in power, maybe 1 watt if you're lucky. But what you're going to do is you're going to run the tubes a lot hotter and they're going to wear out faster. That's why the bias point is very important on that. So that's where this ended up with. So here's our final design. And because it's idling at that lower wattage, that 17 watt to 18 watt range, I could actually plug these in and they will work. But they'll be running at a higher percentage of their maximum plate dissipation than these are. And you really don't see a big difference in performance. Now, even though we were seeing 2% distortion, the sound on this thing is incredible. As a matter of fact, to your ears, at least to my ears when I listen to it, it has a much sweeter sound than a much cleaner solid state amplifier. So a lot of the amps we test are, in the 0.01% distortion at full power, or 0.05%, the very, very low distortion when you compare it to these. But yet the sound of this is much sweeter to my ears. I love the sound of this. I actually started this video 3 or 4 times, and then before I started, I just said one more song. I want to listen to one more song on this, and I just kept listening to it because it was such a pleasure to listen to the sound of this amplifier. And that's the magic of vacuum tubes, I guess. And it's also nostalgia for me because this harkens me back to the days of working on the old jukeboxes with my cousin and listening to some of the older vacuum tube gear that we had, and they all had that type of sound, which to me is a very pleasant sound. It's not the cleanest, but cleanest, purest, most accurate sound isn't always going to be your favorite depending on who you are. Everybody's ears are different. That's the beauty of audio, is the audio hobby is subjective. It's open to interpretation, what you like the best. So that was my reasoning for why we went with what we went. Now here's the thing. For this to be absolutely perfectly like it was when it was designed, we would need to have the correct output valves, and we would need to return the circuit to its original design. We're going to get the other amplifier, and I'm going to get it to a working state so we can use it. We're not going to worry about the tuner on that. I'll do that off camera because you saw that all on this one. That tuner's in much better shape than this one was. And what we're going to do is we're going to try something different. This was designed to be used with an EL37. The EL37 is a special tube. It's an old design, and they're very desirable, and I looked at some online. I was going to try to purchase some, but from a reputable dealer, these things are going for over $200 US each. That's a ridiculous amount of money for basically a variant of a 6L6 type vacuum tube. So luckily we had this little article on the Valve Museum, and I printed it out because it's interesting. And it goes on, and I'll read it. You guys have your mothers read you bedtime stories when you were small? I'm going to read you a bedtime story so you can go to sleep. The EL37 audio output valve is one of the classic valves, and its predecessor was the EL35. At a time of generally low power audio amplification, these valves used in push-pull could deliver up to 69 watts at 2.5% distortion. The EL37 and EL31 are both 25 watt anode dissipation output valves, and the 6L6GC is higher than that, by the way. From the mid-1940s, the main difference is the EL31 has the anode brought to a top cap, so it can run it up to 800 volts. It runs really high anode voltages. So this one does not have the top cap. It actually has pin 3. It's the same pinout as a 6L6. It is also, by the way, a true pentode. It is not a beam tetrode or a beam power tube or a beam pentode, however you want to word it. If you guys don't know what I'm talking about with that, go back to my Fisher X101C video series, and where I actually disassembled a 7591 beam power tube, and we looked at that versus an EL34, which is a true pentode tube. This is similar to an EL34 in that it's a true pentode, but it's similar to the 6L6 in that the suppressor grid is internally connected to the cathode. So the cathode and the suppressor grid are both on the same pin 8, whereas the EL34, that suppressor grid, they moved it to its own separate pin, pin 1. Pin 1 is not used on these. Keep that in mind as we read. This gives higher output power. Mullard also described the EL37 as suitable for use as drivers for bigger tubes. Okay. At 11 milliamperes per volt, it is almost twice the value of the KT66 and the 6L6. So remember, these guys are kind of similar. The KT66 is similar to that 5881 we were looking at, and the 6L6 is a little higher power than the KT66. A Mullard engineer said that EL37, that unlike similar valves, it only needs a whiff of signal to drive it to full output. And that's one of the things with this tube. It has a different characteristic than a 6L6, so you have to design the circuit a little bit different, which is how this one was done. Goes on to say, this valve was rendered obsolete in 1954 with the introduction of the EL34, and that's a very common tube. A lot of you who play Marshall amplifiers and so forth should be familiar with this, or that has the original, like the Dynaco ST70s. There's a lot of famous amplifiers out there that use these EL34s, but they also have that GM of 11 milliamps per volt. So what that means is if we didn't have that extra pin on this amp, look at my last video on this, if pin 1 wasn't being used as a tie point for other circuitry, we would be able to wire pin 1 to pin 8, and we would be able to plug a set of EL34s, which I just so happen to have some in stock here. And these are rated power-wise very similar to the 6L6GC, but with much different biasing and gain characteristics. So we're going to try to wire these. We're going to move the wiring on that other receiver, and we're going to rewire it to take these, and we're going to use the original circuit design, and we're going to compare the sound of that amplifier to the sound of this one, which is, in my mind, this is a benchmark. It sounds wonderful. Now, if you remember, we were originally fitting these 6.3PE Russian vacuum tubes in there. And if you remember what I said at the end of the video, they were starting to just barely red plate. After they've been running for a while, right in the corner there at that seam, right in here, you'd see a little bit of red plating start. And they tout these as 6L6 replacements. And in fact, they are exact replacements for 6L6. Very, very similar anyway, and should replace them. The problem is the suffix. It's a 6L6gb. What is a 6L6gb? Well, let's go back to our GC. Here is a 6L6GC. Here is a 6L6WGB, which is similar but slightly smaller. Don't pay attention to the glass bulb, just look at the internals. But here is an original Sylvania out of a Seeburg jukebox, 6L6GB. So 6L6GB, see it? Black plate, very nice tube. I have a pair of these out of a Seeburg jukebox amp. And take a look at the difference. Big difference in size, isn't it? And if you compare it even to the 5881, it is smaller a little bit. It's got a little bit taller, but narrower anode. And this one has a shorter, squattier. So these are kind of similar. These cannot handle the voltage that these can, but they handle similar dissipation, but they're not exact copies of one another. If you look at this Russian tube, look at that. This is actually a 6L6gb. And these have a much lower plate dissipation than the GC, and they don't have as much room for overdriving them. These are pretty robust tubes. You can drive them higher than they're rated, and a lot of them will handle it for a long time. You try that with these, and they will wear out very quickly. Same thing with these, and that's why this was red plating. So long story short, they came with these plugged in. The bias was actually set for something to handle this kind of power, but with a different gain curve and everything, and a different bias voltage requirement, meaning none of these before you will work properly with the circuit as the way it was. But back to what we were originally saying, if we put this in, we should be able to get it to work like it did with the EL37, and it should sound very similar. Now, one other thing that they did in the other amplifier, here's what they had in the other amplifier. And these are Shuguang, I think that's how you pronounce it, made in China, 5881s, and you can see they're kind of discolored a little bit from the heat, the lettering. And if you match that up to the Chinese tube, it's similar. If you match it up to the GB, very similar. So really, they're calling this a 5881, but it's more of a 6L6GB type tube. And this is what was in there. Why do you think this one didn't red plate and burn up on the other amp? Well, the reason was the rectifier tube that it came with. Somebody put this one in place of it. What they're supposed to have in them, this is a 5U4, this is a 5V4. See the difference? Big difference, isn't there? This won't handle as much power as this. However, the voltage drop that this one has is extremely low. It's maybe 10 volts or 12 volts, something like that. The only tube, the only vacuum rectifier like this, at this size and so forth, that has a lower voltage drop than this is the GZ34 or the 5AR4. This is second only to that. And this one has a huge voltage drop, somewhere between 45 and 50 volts. What does that mean in the grand scheme of things? Well, what that means is when you plug this in, you automatically reduced the amount of voltage on the plates or the anodes of these tubes, which will automatically make it bias lower and have a lower dissipation. So they probably got away with using these smaller 5881s by substituting a larger and more inefficient rectifier tube, and that's why they did that. So once again, I'm going to put this one in there, and then we're going to rebias, or just restore the amplifier to its original factory design, and then we're going to put those EL34s. So I know I'm going on and on and on about this and prattling about it, but So that you understand why this all is important, I wanted to explain it all. And hopefully, when we're done, we'll be able to do a comparison between the two amps. So we're now on the second amplifier, and we're testing to see if we put the EL34s in there, if it will work by rewiring. So what you see here is we wired pins 1 and 8 together, because pin 1, remember, on the EL34 is your suppressor grid. And on this side right here, if you remember, pin 1 was being used as a terminal tie point. So what I did was I have a single terminal strip here that I mounted up here, and then I just relocated that circuitry from here over to here. And that allowed me to jumper these two together, and now we can use the EL34. Now when I tested it, here's the problem we ran into. I'll show it to you. So everything else is stock. So we have the original, here's your 400 ohm resistor down here. You can see it. And I'm going to power this thing up, and I'm going to come back in a minute and I'll show you what's going on. Okay, I had to turn out the lights for this, but do you see what's going on right there? This is what we call red plating. So you can see the anode of this tube right here is turning like an orange color. I'm going to shut this off right now because we don't want to leave it that way. It takes a couple of minutes for it to happen, but it does happen. Now, let's take a look at why. Now this voltage you're looking at on this meter here is the voltage between the anode and the cathode of one of the output valves. And if we look at this meter up here, this is the voltage drop across the winding for that particular valve. So going from the center tap of the output transformer to the anode tap, you have about 8.6 volts. So let's do the math. Okay, 8.6 volts divided by 119.4 ohms. That's the DC resistance of that winding from the center tap of the output transformer to the anode tap. And that equals 72 milliamps. That's a lot of current. And if you times that by that 393 volts, you can see that it's running at 28.3 watts of idle current. 28 watts is way too high. Let me shut this off now. For an EL34 to be just sitting at idle. However, here's the strange thing. I'm going to turn it on for a minute, and we're just going to look at the output. Let me get the glare out of here. I'm going to turn the amp back on so you can see it's warming up. And now that it's warmed up, if I turn this up, you can see I get my clipping. It's pretty symmetrical, and it's a nice clean waveform when I get down to about, and you can see it was running about 31 watts. Now it's at 29 watts. So it's putting out full power, and you can see it's pretty clean. Now, let's see what happens. I'm going to shut this off again. Let's see what happens if we increase this resistor. So, see this resistor right here? Once it focuses, that 400 ohm resistor, we're going to change. So if we back up here, that 400 ohm resistor is this guy right here. And remember, in the parts list, it said it can either be a 400 ohm or a 920 ohm. So let's just see what happens if we substitute a 920 ohm resistor. Okay, I now have a 910 ohm resistor. I don't have any 920s because that's kind of an odd value, but 910 ohms, that's very, very close. So let's see what this thing comes up at with the bias now. Sorry about the glare. There, can you see that? And you can see as this thing warms up, as those 12AX7 filaments heat up, you see the voltage drops. And if you look up here, it was closer to 8 volts or so. If you look now, it's about 6.5, 6.6. It kind of jumps around a little bit. It's 6.6 volts, and you can see 415. So let's do the math. 6.6 volts divided by our 119.4 ohms equals 55 milliamps now instead of 70. And we times that by 413 volts that we have now. And it's, instead of 28 watts, it's still high, but it's at 22.8 watts idle power. So, so it's more respectable, but it's still too high. But more importantly, now if we do our test, watch what's going to happen to our waveform. As we get up near clipping, you see what happens right there? We're starting to get crossover distortion. And even as we back down, the clipping's pretty much gone, but we still have the crossover distortion here. And when we go down to the 400 ohms, that crossover distortion disappears altogether. So what that tells me is if we increase that resistor even more, it will bring the bias down to a respectable level. However, we will get pretty serious crossover distortion. In other words, the bias has to be there for this particular circuit to work this way. So what does this all mean? So the bottom line is we don't have the proper ingredients to run this thing the way it should be. In other words, something's got to give somewhere. Either we have to modify the circuit like we did on the last amplifier, or we have to modify the output transformer. See, part of what's happening here is you could go to a different impedance of output transformer and that has a different DC resistance, and it would be a different impedance ratio, and possibly you could get it to bias better. But this circuit just kind of has to work the way it is. So long story short, even the EL34 does not work the way that it is. Now let's do one more thing. I now have the 400 ohm resistor back in, and you can see we're running at about 122 volts of AC mains. Let's bring that down to about 117. Let's go down a little bit right there. 116.8. So closer to what you would have seen back in anywhere between 110 and 117 is what you have seen in the 1950s. And look what happens with the 400 ohm resistor, not even the 910 ohm. You can see we now have about 8.7. 8.7 divided by 119.4 times 378 volts is what our B plus is now. And it's still 27.5 watts. It's still a little bit running a little bit hot. And if we look over here, not really getting much crossover distortion until you get really heavily into clipping. So it's still nice and smooth, you can see. But you can see your mains voltage does make a difference in the bias. And probably if I went down even further, let's say 114.8. Now we've gone to 8.6 and 371. And that's probably going to be closer to maybe 25, 26 watts, something like that. So really, there's a combination of things working against us on this design, is what I'm finding out the more I work with it. That is, first of all, is the actual vacuum tube that they used in this originally. When, let me turn this off. They originally had this thing spec'd out for an EL37 in this one, if you remember. That's what it says on the chassis, on both the chassis. The schematics, however, said KT66 and EL34. And I'll tell you, these KT66s, again, can handle not a lot of watts, but they can handle high voltages pretty well. And the old saying, they don't make them like they used to, I think that's part of the case there, is that these older valves could handle higher plate dissipations better than the modern ones. At least that's my theory on this. Now, if I put a 6L6GC in here, it'll probably work and it probably won't be any problem. It's still running it hot, but you could run it on a 6L6GC like this with the original circuit. But I would not recommend putting a 5881 or this EL34, obviously is not happy, or anything like that, because they just can't handle that kind of bias. And you can see if we go to a lower bias the way it is, you're going to have that weird looking crossover distortion. So put a big tube in there, and or put our modification. So I think you know where we're going to have to go with this. So we did the experiments, and bottom line is this amp will run better with modern vacuum tubes if we do my modification on there. So that's what I think I'm going to do to this one. Okay, we have our little mod in there just like the last amp, and now you can see our voltage is 5 volts and our B plus is 411, and it's coming out right around 17 watts, which is right where we want it to be. And I've removed the EL34s because, believe it or not, those EL34s just did not work very well. They had asymmetrical clipping. I don't know if it's because these tubes weren't very well matched. And to just show you here, I have the EL34s fitted back in there just for a minute, and I'll show you what I'm talking about compared to those KT80 or the KT88s, the 6L6gb 5881s, whatever you want to call them. It looks good here, but as soon as you start getting up towards clipping, you can already see right there we have crossover distortion, and you can see how it clips really hard on the top before the bottom starts going, and then that crossover distortion gets really bad. Now let's compare it back to those other ones now, the 5880 ones. So here's the 5880 ones, and you can see I can take it all the way up to clipping, and you can see how perfectly symmetrically it clips, and you can look, there is no crossover distortion. And if I bring it just down, see how perfect that is? So really, those EL34s, either they're not a good pair of tubes. I got these low cost online, eBay, so that might be an issue. Or it just might have something to do with the characteristics of the EL34 compared to those 5881s with that bias that I have in there, that bias mod. Hard to tell. I just know that it's much better with the original 5881s fitted in there. So I just thought I'd show you that. I knew I'd get questions if I didn't actually show it. So I did try the ones that came with this, and this one right here has a short in it. It kind of cuts in and out, so I have a feeling this thing was running really hot from when they got it. So we have the correct 5V4 rectifier, we have the 5881s, we have good bias, and we have a really nice signal. So here we go. And you can see how nice and clean that is till it clips. And it starts clipping not perfectly perfectly symmetrically, but not bad. And you can see it's sticking around 26 watts, kind of like the other one. So yeah, it's working really well. Unfortunately, that's the way we have to run this thing. And I think it'll last a very long time like that, which is a good thing. And it'll be easy on the valves, and we can put any type of valve in there we want. We can put a 6l6gb probably. It would be running it a little hot. Those stock 5881s, a 6l6gc, probably a better quality set of EL34s because this one has the jumpers in it the way it should. So if you had a good quality set of those, we could probably use them. You know, this video kind of reminds me, now that I think of it, any of you read a book called Zen and the Art of Motorcycle Maintenance? Kind of a strange read there, but this is almost like Zen and the Art of Vacuum Tube Balancing or Biasing. Maybe I should call that's what I should call this video. Zen and the Art of Vacuum Tube Biasing. I don't know, or something like that. Anyway, enough silliness. So, as always, I think I'm going to end this video here. We have a lot of things coming up. I'm not sure which one I'm going to go with next, but whatever it is, it'll be pretty much of a departure from this vintage of gear. And while we decide that, and until we meet again, I'm going to wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Take care. Bye-bye.